Just a quick recap of what we have done in previous classes. We started with the macroscopic balance, in which the extensive property of a system, how would that change inside a control volume as a result of unsteady state effect and as a result of convective motion of fluid coming into the control volume. Based on that, we have started with an equation which looks something like this, that for a control volume, this is the expression with which was the starting point of all our previous discussion, where the dn dt is the total rate of change of an arbitrary extensive property of the system. The second term is the time rate of change of the extensive property n, it could be anything within the control volume, and the corresponding intensive property is eta. So, eta is nothing but n by m, where m is the mass. So, eta is the intensive property corresponding to the extensive property denoted by capital N. And the last term, this term on the right hand side gives us the net rate of efflux, that is the algebraic sum of inflow and outflow of the extensive property N through the control surfaces. So, with this equation we took this n in the first case to be the mass of the system, and if n is the mass of the system, then obviously the corresponding intensive property would simply be equal to 1, and the equation which we have obtained out of that is nothing but the for this case what we get is the conservation of mass, equation of conservation of mass, or the integral form of the continuity equation. In the second part, we take the extensive property to be equal to momentum, such that capital N is now the momentum. So, therefore, the corresponding intensive property would simply be equal to the velocity of the control volume. So, if N is equal to P, where P denotes the momentum, therefore, the corresponding intensive property would be V, and the dn dt, which now becomes equal to dp dt, would simply be the time rate of change of momentum, which is nothing but the force acting on the system. So, here also instead of eta, we are going to put V, the velocity, and therefore, this is going to be the unsteady state term, and this is the net efflux of momentum through the control surfaces into the control volume. So, dn dt system is when at the limiting condition when the system and the control volume coincide, and in that case dn dt would simply refer to the forces acting on the control volume. So, when we have forces acting on the control volume, the relation that we have obtained is the force acting on the control volume is equal to the time rate of change of momentum of the control volume and the net momentum efflux into the control volume, and the forces are identified as either the surface force or the body force. The common examples of surface forces are the pressure and shear, whereas an example of body force could be the gravity force acting in the system. So, this equation is known as the momentum equation, or rather the integral form of the equation of motion. The points to note here are that all velocities that we refer here are measured relative to the control volume, and by convention mass in is always taken to be negative because of the dot product of velocity and the area vector, where the area vector is always directed perpendicular to outwards, perpendicular to the control surface, and mass out would be positive. Starting with this and with some more simplifications, we have ultimately obtained an ordinary differential equation, and where u is the free stream velocity, theta is the momentum thickness that we have earlier derived to be equal to this, and del star is the thickness, is the displacement thickness, which is obtained previously in this form. So, the beauty of this equation is that first of all it is an ODE, and it does not say anything about tau w, the nature of tau w. So, whether it is laminar flow or turbulent flow. So, therefore, this equation in the momentum integral equation in its present form is equally valid both for turbulent flow and for laminar flow. And since we have the variation of the free stream velocity incorporated into the equation, therefore, this equation is also valid for cases in which it is a curved surface such that the free stream velocity is also a function of the axial position. So, this is a very general equation, and we have seen the use of this equation in solving some of the problems that we have done before, and the final form for the case of flow over a flat plate that we have obtained in the previous class, where delta by x, the growth of the boundary layer as a function of axial position and as a function of other parameters, including the imposed condition of the approach velocity, which is embedded into Reynolds number, and the properties of the fluids also incorporated in the Reynolds number, they are of this form. If you recollect the exact solution for flow over a flat plate, which the exact solution which is also known as the Blasius solution, the form of the equation was exactly the same, only difference is the variation in the value of the constant. In the case of exact solution it was 5, whereas in the case of the momentum integral equation it was 5.48. Similarly, we have defined what is the shear stress coefficient, defined as tau w, the wall shear stress, divided by half rho u square, where u is the free stream velocity. So, following this and incorporating the expression of delta from here, we have obtained the expression for the shear stress coefficient to be equals 0.73 by Rex, and our result from the exact solution of Blasius was the same form, only difference is in the value of the constant. So, we are getting we can predict the growth of the boundary layer within an accuracy of plus minus 10% when in comparison with the Blasius solution. And similarly, the coefficient of friction, the friction coefficient is also very close to the friction coefficient obtained from the exact analytical solution. Now, considering the problems which one encounters in solving a partial differential equation, even for the simplest possible case of flow over a flat plate, the approach of momentum integral equation is therefore is quite helpful. And we would see later on that since this equation takes into account the possibility of having turbulence present in the system, the range of applicability of this equation is much more, and it is quite easy to handle in comparison to the exact analytical method. So, what additionally we have done is that we have seen how to first assume a possible velocity profile inside the boundary layer for the case of laminar flow, and they were expressed, for example, in the previous problem as a polynomial a plus b eta plus c eta square, where eta is the dimensionless distance from the wall defined as y by delta, where y is the distance from the wall and delta is the local value of the boundary layer thickness. So, if Vx by u, velocity inside the boundary layer divided by the free stream velocity, so that is the dimensionless velocity defined as Vx by u, if it is expressed as a plus b eta plus c eta square, then using the boundary conditions, the relevant boundary conditions, and the relevant boundary conditions are no slip at the solid liquid interface. That means Vx by u is 0 when eta is 0. Secondly, the velocity approaches the asymptotically, the velocity approaches the free stream velocity at the edge of the boundary layer, and at the edge of the boundary layer eta is simply equal to 1, since y is equal to delta. So, at eta equals 1, that means at the edge of the boundary layer, the value of the dimensionless value of the velocity would be equal to 0, and also the gradient of the velocity at that point, that is at eta equals 1, would also be equal to 0, since the velocity approaches the free stream velocity asymptotically. So, using these conditions, we were successful in evaluating the values of A, B and C, the constants A, B and C, and we have obtained an expression for the velocity. The expression for velocity, when substituted in the momentum integral equation, gave us the results that I have just described, that is the, and we could compare, we could benchmark the utility, the accuracy of momentum integral equation by comparing it with the results which were analytically obtained, and we compared the expression of delta and we compared the expressions of CF. In both cases, they come out to be very close to each other. The reason for that is, since boundary layer is extremely thin, and if we could correctly identify what would be the boundary conditions at the solid liquid interface and at the edge of the boundary layer, then what happens in between is probably going to have very small effect on the overall growth pattern of the boundary layer and the value of the friction coefficient. So, this is the reason why momentum integral equation is successful in providing an expression, correct expression for delta and for correct expression for CF. So, these are reasonably accurate, within 10% accuracy, considering the less amount of effort that we have to provide, we have to do in terms of getting the solution. This is a welcome change. So, from now onwards, we will restrict ourselves to the solution of boundary layer phenomena using momentum integral equation. Before I move on to the treatment of the turbulent boundary layer, which was not possible using any analytic method, we would, in this class, we would first try to see how to solve one more problem where the profile of the boundary layer, the profile of velocity inside the boundary layer is provided, and with that velocity profile, we would again see how close we are to the actual value of the boundary layer. So, the first problem that we would do in this tutorial class is, given a velocity profile, can we find out what is the expression for the growth of the boundary layer and what is the expression for the friction coefficient, normally denoted by CF. So, in this problem, it has been mentioned that the velocity profile inside the boundary layer is simply linear. So, that is the simplest possible variation. So, it varies with a value equal to 0 on the solid surface to a value equal to v at the edge of the boundary layer, where this velocity is essentially the free stream velocity. So, if I express the non-dimensional velocity as Vx by capital U, where capital U is the free stream velocity, then Vx by U has a value equal to 0 at eta equals 0, and Vx by U would be 1 when eta is equal to 1, that means at the edge of the boundary layer. Remember that eta is defined as y by delta, where delta is the local film thickness. Therefore, the simplest possible profile that we can think of is Vx by U is simply equal to eta. The functional form of the velocity variation inside the boundary layer is Vx by U is equal to eta, and we would quickly see how this can be used with the help of momentum integral equation to obtain an expression for delta, the thickness of the boundary layer, and an expression for CF. So, we start with our analysis of the assumed profile that Vx by U is simply equals eta, and see from there how to proceed in order to obtain the expressions of delta and CF. So, we start with the momentum integral equation, which is tau w is rho u square d del dx from integration from 0 to 1 u by capital U, the velocity inside the boundary layer, and the free stream velocity 1 minus small u by capital U d y by delta. and we note here that it has been given that u by u is simply equal to eta, that is, a linear velocity profile is prescribed for this condition. So, this can now be written as rho u square d del dx and beta, where this beta is essentially this definite integral. So, beta is going to have just a numerical value. So, since u by u the velocity profile is given, so we can now find out what is going to be the definite integral, which is a very simple step d eta. So, this is from 0 to 1 eta 1 minus eta d eta, and this would, once you integrate, this would result in the numerical value equal to 1 by 6. So, this beta is therefore equal to 1 by 6, since we have assumed a linear velocity profile. And also, if the fluid is Newtonian, then wall shear stress can simply be written as following Newton's law of viscosity, del y at y equals 0. So, this is for a Newtonian fluid, and if I express everything in terms of the dimensionless velocity, which is this, and the y is transformed to eta, then what I would get is simply the dimensionless velocity and the dimensionless distance. Everything is evaluated at y by delta to be equal to 0. In other words, this now becomes mu u by delta in del u by capital U by del eta at eta equals 0. Now, since the velocity profile is provided to me, the velocity profile is provided, so this is simply going to be equal to 1, and therefore, the expression for tau w would be equals mu u times delta. So, what I have then is, I have found out what is going to be the left hand side of the momentum integral equation, mu u by delta, and the right hand side of the momentum integral equation, which is simply going to be 1 by 6 rho u square d del dx. So, this therefore is simply an ordinary differential equation, and the final form of the ordinary differential equation would simply be equals times 1 by 6. This equation can now be integrated, and once you integrate this equation, what you would get would be del square by 2 equals 6 mu by rho times capital U times x plus c, where this c is the constant of integration, and c can be evaluated through the use of the boundary condition that at x equals 0, that means at the start of the plate x equals 0, delta, the thickness of the boundary layer, must be equal to 0. So, using this boundary condition, you would get the value of c to be equal to 0, and thus this delta by x would simply be equal to 12 mu by rho u x, or delta by x to be equals 3.46 by root over r e x. Similarly, if you find out the expression for Cf by definition, which is equal to tau w by half rho u square, this would be 2 mu by rho u delta, and when you put the expression for delta from here to this, what you would get is Cf equals 0.577 by root over r e x. Compare this with the Blasius solution, where the form would remain the same except the constant would be 5.0. Again, the form here would remain the same, the constant is going to be equals to 0.664. So, here you see that even a very simple approach, the simplest possible velocity profile, if you assume that, you still are not too far off from the analytical result which was obtained by solving a partial differential equation numerically and using the concepts to obtain the exact form of the boundary layer growth or that of CF. So, this again underscores the utility of momentum integral equation in solving any problem. So far we are limiting ourselves to laminar boundary layer, and this is going to be the method of choice for all solutions from now on. I would also solve one more problem regarding the involving the use of momentum boundary layer, use of momentum integral equation, and this problem is essentially a flow, again flow over a flat plate, and there not only you have to obtain what is going here, also a profile would be provided. If the velocity profile is not provided, you can assume a polynomial and find out what is going to be the variation, of the velocity as a function of eta, the dimensionless distance from the wall. And in this specific problem, it was asked what is the maximum value of the boundary layer thickness and where do you get the minimum value of the wall shear stress. So, if I have flow over a flat plate, at which point you are going to get the maximum thickness of the boundary layer, and secondly, where are you going to get the minimum value of the wall shear stress. See, the first question is obvious. If there is a flow over a flat plate and since the boundary layer keeps on growing, you would get the maximum in the boundary layer thickness at the end point of the plate. So, when you reach to, since the boundary layer keeps on growing, when you reach the end of the plate, the thickness of the boundary layer is going to be the maximum. So, that is an obvious answer, but we would still see if we get if we get the same value. But the question of shear stress is not that straightforward, at which location the shear stress is going to be minimum. So, that is the second part of the problem, and the third part of the problem is find out what is the total force exerted by the fluid on the solid plate. In other words, in order to maintain the solid plate at a static position in a flowing fluid, what force must be exerted. Okay. So, that is the third problem, third part of the same problem. So, given a profile, find out the maximum value of the boundary layer thickness, find the location and magnitude of the minimum wall shear stress, and an expression for the total force experienced by the solid plate due to the motion of the fluid. That is the problem which we are going to solve now. So, here also it has been mentioned that the velocity profile, which is Vx by u, is of this form: 3 by 2 y by delta minus half y by delta cube. So, this is the profile which has been provided to us, and using the methodologies already prescribed here, the momentum integral equation, it would be easy for you to obtain, but I would still request you to do it on your own. You would see that delta by x would turn out to be 4.64 by root over r e x. The kinematic viscosity for the fluid is given as 1.0 into 10 to the power minus 6 meter square per second, and the length of the plate is 0.1524 meters, and width of the plate is 0.914 meter, and the velocity, free stream velocity, is provided as 1.22 meter per second. So, this is free stream velocity, and since its flow over a flat plate, this is also equal to the approach velocity. So since delta by x is given in this form, so you can see that the expression is simply going to be x by root over r e x, and the delta max would simply be equal to at x equals L. That means if I have flow over this, then of course the delta max is going to be at x equals L. So x equals 0 to L. So therefore delta max would be equal to at x equals L. So when you plug in the values, delta would be 4.64 and 1 into 10 to the power minus 6, which is the kinematic viscosity, meter square per second. The length is simply going to be 0.1524 meter, and the velocity is, free stream velocity is 1.22 meter per second, square root of that, and your delta max would turn out to be 1.657 into 10 to the power minus 3 meters, or roughly it's close to 2 millimeters. The wall shear stress, on the other hand, the expression for that, the wall shear stress, so this is why it's going to be plus mu times del Vx del y at y equals 0. When you transform it to in terms of the dimensionless quantities, it would simply be mu u by delta d Vx by u dy by delta, and it is evaluated, wall shear stress is evaluated at a point where y by delta is equal to 0. So therefore your tau w would be equal to mu u by delta, and for this we plug in the expression of Vx by u that has already been provided to be 3 by 2 y by delta minus half y by delta cube. So when I plug this in over here and take the differential, what I would get is 3 by 2 minus 3 by 2 y by delta square. Everything is evaluated at y by delta to be equal to 0. So this tau w would therefore turn out to be 3 mu u by twice delta. So tau w minimum would be at a point where delta is maximum. And when you, so tau w minimum would be equal to 3 mu u by 2 delta max, and when you plug in the values of delta max, mu, u and delta, the numerical value of this you are going to be equal to 0.552 Newton per meter square. So therefore the minimum value of the wall shear stress will be 0.552 Newton per meter square, and it would take place where x is equal to L. So at the edge of the boundary layer, you get the at the end of the plate, the location at the end of the plate would provide you with the maximum value of the boundary layer thickness, and also at this point you would get the least value of wall shear stress. So wall shear stress is a monotonically decreasing function of distance, and delta is a monotonically increasing function of x. So since tau varies from point to point, therefore the total force exerted by the fluid on the plate will also vary with position. So to obtain the total force, since we know that shear stress is equal to force per unit area, so the total force on the plate would be provided if we integrate tau w over the entire area. So the force by the fluid on the plate F, if we denote it by F, would simply be integration tau W dA. Now tau W is not a function of W, the width of the plate. So if I take the W outside, it would simply be integration from 0 to L tau W times dx. So that would be the expression for force exerted by the fluid on the solid plate. So which if we do it here, so the force Fd, and the term d here stands for the drag force. So this is a force due to the friction of the moving fluid over the stationary plate, commonly denoted by drag force. The expression of that would be the integral over the surface tau W times dA. So if I express it, since we understand that tau W does not depend on W, so it's tau W times dx, and the W can be taken outside. And what you do here is you are going to put the expression of tau W in here, and therefore you would get from 0 to L 3 mu u by 2 delta times W dx, 0 to L 3 mu u 2, and the expression of delta from the previous page, where the expression of delta was 4.64 x by root over Rex. If we put it in there, what we would get is into 4.64 root over u by nu x times W times dx. So tau W, the final expression would be integration 0 to L 3 mu u by 9.28 root over u by nu x times dx. So the rest is simple. You can simply do the integration over the entire length of the plate from 0 to L and obtain an expression for the force on the plate, and the final expression for tau W can be obtained from there, which I again leave it for you to find out what would be the final expression for tau W. So this again underscores the advantage of using the momentum integral equation. Now I think we are confident enough that we would be able to try to solve turbulent flow inside a boundary layer. Now the moment we introduce the concept of turbulent flow, the moment we allow turbulence present in the system, there are a few things which we have to keep in mind. First of all, the expression of tau, the shear stress, to be, if it's a Newtonian, to be equals minus mu times velocity gradient will no longer hold. Okay? Because in turbulent flow, the transport of momentum is not only by the molecular motion, it's the actual physical motion of packets of fluid having different velocities from one point to the other. So the momentum transfer will no longer remain a molecular phenomenon. It will also involve the formation of eddies or packets of fluid which will move with a specific momentum and therefore transport momentum in between layers in a fashion that we did not encounter or we did not envisage in our treatment of the laminar transport of molecular momentum or shear stress. In other words, the shear stress in turbulent flow would be much more significant as compared to the laminar flow. So we have to keep in mind the molecular transport as well as the convective transport of momentum. The moment we bring in the concept of eddies, then we would see that the stresses that we have encountered in laminar flow will have to be modified by incorporating additional terms in the Navier-Stokes equation, collectively known as Reynolds stresses, which depend on the locally fluctuating component of velocity as a result of turbulence present in the system. So it's a very complicated case. Whenever we talk about turbulence, mathematically treating, I mean, it is possibly easier to visualize what happens in turbulent flow, but whenever you try to explain it mathematically, it becomes very complex. So here again, the use of momentum integral equation and the approximations that we would use would definitely be helpful in obtaining closed form expressions of shear stress and growth of boundary layer, the expression for drag force, and so on in turbulent flow. That's what we are going to do in the next class.